especially focusing on the token communication applications. Let me briefly introduce myself. I've been working on two fields. My focus is two fields. One is machine learning for communication. The other one is communication for machine learning, especially distributed machine learning. And recently I've been focusing on distributed inference while achieving high communication efficiency. Let me also briefly introduce our research group at SUTD. We are working under the Future Communication R&D program supported by the IMDA Singapore, which is the largest grant, amounts to 70 million Singaporean dollars, which is largest in the area of wireless communication. And today, another professor, Bin Chen, will be introducing more details on this FCP program in this afternoon session. So FCP is led by our director, Professor Tony Quick, and we have two deputy directors, Professor Bin Chen and me. And within FCP, we have two strategic areas. One is mobile communication, and the other one is NTN. For the mobile communication, we've been focusing mainly on the Open RAN in the last 4 years. And then in the next phase, we'll be foreseeing, starting from the late next year, we'll be focusing mainly on the transformation from the O-RAN to AR-RAN. In parallel, the NTN evolution from the fifth generation to the sixth generation. And ultimately, our overarching goal is to create some synergetic effect by integrating these two technology paradigms. So within FCP, our recent preliminary works and initiative is to promoting and facilitating this AR-RAN alliance activities. Especially, FCP is hosting one of the 4 global first AR-RAN Alliance Industry Lab. 3 are in the States, and then AR-RAN Alliance Industry Lab in Singapore is the only one in Asia. And within our AR-RAN Alliance laboratory, we provide the end-to-end solution from the 5G core emulation to the real testing using the user equipment. We also actually, FCP program has been supported by the IMDA. IMDA is not only supporting the research activities, but also managing the frequency licensing in Singapore. So they thankfully allow us to transmit the cellular frequency, FR1 and FR2 band within the campus. So that is very privileged opportunity to demonstrate those real AI application, not only inside some small-scale indoor environment, but also for outdoor and high-stake application demonstrations as well. And one remarkable recent activity is our AR-RAN Alliance demo at MWC last year, which was been focusing on the split model inference while optimizing the model split by predicting the current channel conditions. And actually, the follow-up demonstration will be presenting in the NVIDIA GTC Washington, D.C. actually started from yesterday. So actually, I was asked to choose either the NVIDIA GTC event in Washington, D.C. and this Mobile Korea event, unfortunately conflicting with each other. So I decided to prioritize this Mobile Korea activity. So we've been strongly promoting the opportunities and activities under the AR-RAN activities under the AR-RAN Alliance. AR-RAN Alliance is strategically focusing on 3 key areas. One is the AI for RAN. In other words, utilizing AI for enhancing the communication spectrum efficiency. The second one, AI and RAN, is utilizing the multifunctional future AI-based RAN to support both AI application and RAN application while orchestrating their communication and compute resources. The last one is AI on RAN activities. Within the AI on RAN working group, we are focusing on how to better support the AI application by leveraging this AI native RAN architecture. And this is a working group where I'm vice chairing. So today, I'd like to focus more on the AI on-RAN activities. So for example, what could be the high-stake application we can foresee in the next generation communication systems within this AI on-RAN territory and domain, so for especially in the area of Gen AI and large language models. So to answer this question, it would be better to first understand the current trend of the AI processing. So recently, we are witnessing the generative AI, and then now people have started discussing about the future of this Gen AI, especially physical AI and many other, all of which are based on the transformer-based architecture internally, and then their internal unit AI processing is now transformed from the bits to the tokens. So for example, when we see this ChatGPT even pricing unit, is no longer the bit-based and volume-based pricing, but more on the token-based pricing. So considering this trend, the industry has recently pointed out that this could be one major transformation, especially when forcing the next generation communication system. For example, Huawei has been facilitating this new direction since, say, 2 years ago. And recently, MediaTek has also pointed out that the transition from the bit to token will be one of the major key challenges, the major key paradigm shift from the 5th to the 6th generation. And 3GPP, in the last, I heard that last India plenary meeting, they have discussed some opportunity or application of the token communication in terms of the compression, multimodal data compression here. And also, they started discussing the proper traffic model for this new type of communication that has been discussed among MediaTek, ATT, Google, NVIDIA, and other companies as well. So in academia, we have also studied and started studying these activities, actually starting from the semantic communication, and then now have been evolving towards this token communication. One interesting example could be, token is not only the unit of the AI processing, but also across different tokens, we can utilize their intercorrelation as well. So through which we can predict the other token based on some tokens and many other. So one application is a token-based multiple access. So for example, we can intentionally remove some tokens, and while the other user's token can be predicted by other tokens under the same context. So that enables token domain-based multiple access as well, while reducing the communication subcarrier allocations. We can also utilize the token-based processing for better understanding the context information. So for example, if we consider encoder and decoder models are different and heterogeneous, and then we can provide some context information and characteristics of these models to the, say, large language model to fine-tune their presentation or style of speaking and listening, which can be immediately adapt to the current context and environment without any, further adjusting their model parameter, which may take quite a long time. Another application could be the token-based packetization. So for example, if you consider the, say, erasure channel scenario, say, not the entire token can be transmitted over the channel, some of which can be removed. Then in that case, if this baseball, the bet information, bet and stadium information tokens can be transmitted successfully, then it can generate a proper image generation creation. However, if only the bet information and token can be transmitted and successfully received, then the receiver might be confused that with some animal bet image as an example. So by understanding their contextual information, we can prioritize which combination of the tokens can be jointly packetized and transmitted over unreliable and channels, especially under poor channel conditions. And based on this aspect, today I'd like to focus more on introducing some key challenges, mainly 3 key challenges, and introduce 3 possible corresponding opportunities revolving around the AI RAN and token communication. One challenge I'd like to address is the very nature of the dispersed and heterogeneous AI. So for example, when we consider one of the current standard reference design of the AI RAN enabled by the NVIDIA's ARC1 computer, then that can correspond to achieving up to, say, 36,000 TOPS, which is corresponding to 72,000 tokens per second. On the other hand, our current state-of-the-art mobile phones can support on-device AI corresponding to, say, up to 50 TOPS. So given their different level of AI processing and inference capability, how can we better utilize their dispersed and heterogeneous AI compute resources? Is a key question. So one idea is by leveraging their uncertainty measurement. For example, let's imagine that the local mobile devices is equipped with a small language model. On the other hand, the AI RAN is equipped with and hosting the large language model, between which we can utilize both model in different roles. For example, small model is small, so it can generate the tokens with very fast speed. On the other hand, large model is large, so its inference speed is not that fast. However, the large model is more accurate. So considering their complementary role, small model can generate the tokens quickly, and then the large model serves as a role as a validator to reject inaccurate tokens, to resample and replace the inaccurate tokens. So here, this operation can be implemented by leveraging some opportunistic transmission idea. For example, the small model can measure its output tokens uncertainty locally, and then decide to transmit or not based on their uncertainty measurement. So we have heuristically identified strong correlation between the large model's rejection probability and the small model's uncertainty. Leveraging this, we can identify up to which uncertainty threshold the small language model should decide to transmit or not. And the major communication overhead in terms of the payload size is actually the transmission of the entire token distribution defined over the entire token vocabulary in the dictionary. So for example, for the normal large language models, the size is around 32K dictionary size. So given this, not only instead of sending the entire token vocabulary distribution, we can select, say, top K tokens based on some analysis by minimally compromising their accuracy. Then we can achieve up to, in total, up to over 3.6 times token throughput enhancement while achieving almost 99% accuracy. And by skipping over and around 75% of the transmissions. For each transmitted tokens, we can save by reducing and utilizing the top case sampling, we can save over 99.9% payload size, which is also robust to the poor channel conditions as well. And actually, this study has been done in collaboration with Yonsei University. Yonsei team has been extending these activities for the language model-based robot arm manipulator. And then on the other hand, in SUTD, we have been studying a bit more dynamic and interactive scenarios, for example, reinforcement learning-based control. And recently, we are focusing on leveraging and supporting heterogeneous robots and mobile robots. For example, humanoid robots, quadruped robot, and other autonomous mobile robots. They are all equipped with a small model based on their different hardware form factor, and then also equipped with 5G dongles that can be directly connected to the ORU that is connected to our ARN servers. Currently, we are using the H200. And in collaboration with our collaborator, Red Hat, we can optimize and orchestrate their compute resources across different large models. And then based on which, we will implement some joint compute and communication resource optimization through proposing some narrow slicing techniques. So here, for example, when the humanoid robot is perceiving the real environment using multimodal data, then we can decide what kind of corresponding token information can be transmitted to the AI RAN server for better decision-making, or if the channel condition is poor and/or the local decision-making is sufficiently good with low uncertainty, then we can entirely rely on their local decision-making. So, and given which, considering supporting multiple heterogeneous devices, we can optimize at the AI RAN side their compute resources, as well as jointly optimize with their communication resource allocation and/or the access prioritization. So when we started looking into these types of problem, we have encountered these types of fundamental challenge. That is, ARN cannot directly interact with the real environment. So robots can interact with the real environment, but their AI capability is quite compromised. On the other hand, even though the ARN servers and equipment are equipped with a high inference capability, they cannot directly perceive the real environment, cannot affect the real environment through the actual actuation. It does not understand the physics and as well as the channel environment information. So to compensate this problem, to address this problem, we are currently working on augmenting the missing pieces by combining the high fidelity robot simulator and the ray tracing based channel emulation. So for example, the recent state-of-the-art robot simulator can emulate not only the geometric scene, but also their physics modeling and the sensor emulation in real time as well, which is GPU accelerated as well. So for example, this is a vision sensor information, this is 2D LiDAR information, the real scene images, they are all synchronous with high fidelity. This is the real-time rendered image and scene. On the other hand, however, the current robot simulator do not emulate the realistic channel information and environment. So our idea is quite simple. So, we can also leverage the ray tracing-based GPU-accelerated channel simulator in combination with the high-fidelity robot simulator. So here we utilize currently the NVIDIA Sionna simulator for ray tracing. By uploading SUTD campus maps, they can generate a coverage map. To connect this NVIDIA Isaac Sim and NVIDIA Sionna, actually there's a practical engineering issue. Their file formats are not compatible with each other. So in between, we have put the robotic OS server, a small robotic OS server, or a ROS server, that can relay only the dynamic information, time-varying information, for example, the changes of the transmitter and receiver location, while all the other environmental information can be kept as fixed. So in our current preliminary implementation, the Isaac Sim, the robot simulator, and the ray tracing simulator are synchronized for every 1 second to generate their real-time scene and physics modeling emulation, as well as their channel emulation as well. So thanks to the utilization of the relay, ROS relay server, we can directly intervene the environment by controlling the robots using the joypad, as well as we can also impose and apply the machine learning-based controlling or autonomous controlling algorithm directly fed into this ROS server and the Isaac Sim. So the last challenge I'd like to emphasize is that here, all the success of this implementation and application depends heavily on the fidelity of those emulation. So in reality, for example, we can encounter some mismatch between the robot information, their hardware information, as well as the environmental information. So for example, the one in the Isaac Sim currently rendered is different from the actual real SUTD campus picture, right? So to address this problem, for the hardware mismatch information, it can be relatively easily addressed by recasting some information to the robot manufacturer. However, the environmental information is very important and sensitive for the wireless communication channel modeling. However, some information, especially not the geometric information, which is relatively easy to access, but their material information is hardly obtained. For example, in the current indoor environment, there are multiple material information required. This presentation screen and the poster and some speakers, but nobody is providing those types of information. So the recent modern ray tracing simulator can support learning those information, having access to the real ground truth measurement. However, the problem is that the learning time increases linearly with the number of target objects. So if you consider complex and dynamic environment, then definitely real-time operation is not feasible. So our idea is to utilize another vision language model that by leveraging their context understanding. So actually those material information in terms of the permittivity and conductivity are defined, their range are defined based on the ITR document. So we can put those document information to the vision language model as a context. Given this context, we can feed the real visual scene to the model and ask the question, estimate the target object's material information based on within the scope of this context. Then the vision language model can provide at least coarse but instant estimate of those parameters. The beauty is that here the inference time and overhead is independent of the number of target parameters. So by utilizing this, we can provide a good estimate And then we can further fine-tune, treating those estimate as a good initialization. We can also fine-tune those model parameters with much accelerated learning speed. So we plan to extend this scenario to by deploying some real, actual, and more active robot environments. So their task is to identify those surrounding environmental parameters to reach out to the target object locations and capture their sensor information in different modality and feed this information to the vision language model, while the ARN is given this information transmitted from those robots. The ARN can provide and fine-tune those model parameters, treating those source information as a good initialization. All right, so this is actually the end of my presentation. I'd like to conclude my talk by sharing a bit more future, challenging issues. So for example, I have covered some token communication application and opportunities and challenges. However, the very fundamental of the tokens, when you compare the tokens with the real actual bits in terms of the pixel, the raw data resolution or fidelity is much higher than the tokens. So if we aim for some extreme cases of the applications required to achieve very high fidelity, then the performance of the token communication is definitely worse than the classical communication. So we can consider there are hybrid types of communication. For example, for some high fidelity application, reconstruction with high definition, then we can rely partially on the classical communication. While for some poor channel conditions with high efficiency, then we can better rely on the token communication. And in between, we have proposed some idea of how to combine and integrate them together while given the limited resources. On the other hand, the key unique factor of the token communication is the context understanding based on those tokens. So recently, by leveraging this context understanding, there are many interesting agentic to agentic AI and communication as well. So each agent, by understanding their context, it can play a role, a specific role, and between which they can communicate their raw data, multimodal raw data, or their outcome decision making. So model context protocol and agent to agent protocol, A2A, are two promising protocols. However, those designs are irrelevant to the wireless environment, for example, irregular channel, communication efficiency, and many others. So by understanding those different unique nature of the wireless channel conditions and environment, should we simply adopt the existing agentic communication protocol directly, plug and play, or otherwise should we need to design the new, for example, network slices or optimization orchestration techniques for the upcoming agent-to-agent communication is another key interesting topic and question we can raise. Okay, that's the end of my presentation. Thank you for listening.